Good morning from Knoxville, Tennessee, here in the Powermetrix bunker. I'm always amazed. So we evidently are in our 10th week. So we've completed 9 weeks of these, so over 2 months now. It seems like it's flown by every time they tell me. I'm pretty shocked at that. Yeah, we've learned how to do this a lot better. Hopefully, we did have a lot of bumps in the beginning. We've learned a little bit about ourselves, and we learned a little bit about each other. This is some cleaner that, everybody was just talking about how this cleaner stunk, so hardly anybody was using it. And Chris Mullins used it for the first time. As soon as he squirted his hand, he said, "Who used PGA to make this?" Well, we all kind of did the slow head turn to look at Mullins, and that's when he said the 5 words that I guess get you out of a lot of things like that. He said, "Hey, I was in a fraternity." So I guess if you're in a fraternity, that accounts for all that. So we learned a little about Chris on that one. We all made note to ourselves on that. Yeah, we've been doing these this is our 10th week now. So today it's going to be introduction to metering components. What this really is Chris just asked me in a meter school type vein if I would just talk about some of the basic, I'm talking about basic brand new meter tech, both some tips on how to test, some tips on when you're out there in the field what to look for, and just talk about the very basic stuff about being a meter tech. We'll talk about meters, we'll talk about CTs and PTs, and we'll talk about test switches, just the basic stuff this morning. So that's what they asked me to talk about. So that's going to be today. Now, the upcoming ones, the theme that we've got now. It is, since the only meter schools I know of that tentatively could happen will be Auburn and SEMA coming up, but all the rest have been canceled. So we're doing classes similar to what we do at the meter schools. So I'm actually not going to be involved for the next 3 weeks, 3 sessions. And that'll be the engineers, and Chris will handle those. I'm doing this first one. It's hands-on of introduction to meter testing, if you will, or just meter site installations. And then they're going to go into, like I said, they're going to go into classes. You got Thursday, it's going to be introduction to vectors, and then Thursday, then next Tuesday it's going to be CTs and PTs, and then next Thursday it's going to be justification of site testing. Then what are we going to talk about today? We're going to start at the very basics. What is a meter, differences between TR and SC meters, talk about meter sockets a little bit, CTs, PTs, test switch, billing multipliers. So basically what this is going to be is I'm just going to talk about things that I talk about when I'm out there doing the training with folks, and Chris will jump in and he'll ask me questions if it's something he wants me to point out. And if you guys on the chat room start right now, remember there's a little bit of a delay, so jump on there if you want to, if you've got anything, if you've got any pointers or suggestions for the new guys, okay? You veterans out there, go ahead and send us something in that we want to make sure we point out to the guys so they can do their jobs not only better but safer, okay? And I'm going to wait and wrap up with a prayer at the end, so we'll just go ahead and get started in this, all right? So, if you're going to be a meter tech, what's the very first thing? Obviously, meters. So let's talk about the meter, for instance. So the meter, this is actually a snapshot of the meter that's in here, in my socket right here. And you can look at the bottom there. This is at the meter face, and you get a lot of information off of that. You get the meter form. In this case, it's I've got this in a 9S socket. This is a 9S meter. The meter form is very important to you because, you can show up here real quick for just a second. Okay, so what's behind here, and notice when I pull this out too, we're just going to start very basic, right? You want to use a rocking motion to remove or insert a meter. So I'm going to rock it out and pull at the top and pull it out like that. And then when I put it in, I do exactly the same thing, okay? Well, these sockets, these terminals here, right, are different phase voltages and currents. So this is very important that you get the correct meter in the right meter socket. Sometimes it can actually be dangerous if you put it in the wrong one. But for sure, where I usually, just am throwing a for instance out there, if I thought I was one of my stabs on the back of here was making a connection to A phase, it might not be because I've got the wrong meter in there, and I look up and I don't have a phase current, okay? Or it could be I making my connections across there. As I said, it could potentially be dangerous if you try and cram it in there in the wrong one, all right? So the right meter form going in the right socket is absolutely, it's very, very, very important to us, right? Also, you notice here on the face of it, and we'll go back to that. Okay, so it says it's a 9S or an 8S, you know, and the most popular transformer rated meters are going to be your 5s and your 6s and your 9s. And so when I say a transformer rated meter or a TR meter, that means that for that meter, there is an exterior, either potential transformer or current transformer or both that is feeding that meter. Okay, so I'm transforming down, if you will, the voltage or the current down to the levels for a transformer rated meter. And that's why you see just to the right of the form it says class 20. Okay, so this meter is rated for a 20 amp installation, all right? So 20 amps, that class 20 says it's made to operate at 20 amps. If I had a class 200 meter, that would be a self-contained meter. And the difference between a transformer rated and a self-contained meter is, it's just, they're talking about the CTs. Excuse me. The self-contained meter has CTs within the meter itself. So the current that's coming in is the straight current coming in off the service. So I could literally feed 200 amps into that meter, okay? You won't see that on the transformer rated meter because the exterior potential and current transformers are dropping down that current and voltage. Let me grab some water, excuse me. That was good stuff. Okay, so what happens then is, get some coaching from the back. So what happens then is, remember, we're talking about if I'm having my CTs out there, and we're going to talk about in a minute, they're transforming down that current so that there's a couple of reasons why, if you think about it. If I was trying to run my test switches in that at the bottom of that, right below that meter, if I was trying to run really high amperage there, those switches would have to be huge and bulky and beefy to handle current flowing through there. But because I transform down and drop that current down, I don't have to have as big a test switches. It's also easier for me to meter and measure it when it's smaller, right? Because now my bandwidth there is a smaller amount of the highest current that I could have. Since that's a narrower margin now, I can measure it a little bit more precisely. So I do want to have, I want to bring down that current that's going down there. Also, not only just for the size of the equipment, but for safety. All right, so when I'm dealing with the bigger customers and I have bigger potential power up at the top of the pole, I want to transform it down and make it safer for the guy at the bottom of the pole, for you and I. Same thing on the voltages. You know, a typical voltage, let's say a 2 to 1, that means it's going to drop by half the voltage it sees at the top. We'll talk about that a little bit more in a minute. But it is transforming everything down. There's step-down transformers on a transformer-rated site so that where I'm working down there at that metering installation, where the meter and that test switch are, all right, I have lower voltages and lower currents. On the self-contained, like I said, it could be a class 200. That means I got to keep in mind, too, I have a lot more current down there at the bottom of that pole that I'm dealing with. So it should gear me up when I'm thinking about safety. I need to remember that could be a class 200, so I could have 200 amps down there. A class 320 is even higher than that. So you have to be careful when you're down there working. Look at that meter for a second. I mean, it's basic. It should be basic meter tech policy and process that you look and make sure, is that the correct meter that's supposed to be in there? Okay? Now, you'll also notice there as we're moving across there, it also shows the voltages this meter will work with. Sometimes you'll see 120, 480. That means that meter can be used for 120, 240, 480, all the way across from 120 to 480 on the service. This one says 120, 277 volt, 4-wire. Okay? So that gives you the range of voltage that this meter is made to operate in. All right? 60 hertz for ANSI and here in the United States, we work on 60 hertz. So you go into other countries, it might be 50 hertz. But for us, anything that you and I are going to work with is going to be 60 hertz there, okay? Now, TA is test amps. What that means is to test that meter according to ANSI. It gives you now we're talking about that full load, light load power factor test, right? So we're talking about a phantom load test. So ANSI tells you what you should test, what you should set your full load at. And it's saying for this meter, ANSI says, my full load is 2.5 amps. So whenever I set that, then everything else falls in place after that, right? Because I've got 2.5 as my full load, then I know my light load is always 1/10 of that. So the meter tells me per ANSI what my full load should be. Then I know by calculations I take 1/10 of that, and that's my light load. So for this meter, according to ANSI, I should test 2.5 on my full load and 0.25 or 1/4 of an amp on my light load. And then we always know for the power factor test on a phantom load test, the change there is we just make the power factor 0.5 on it. So that's how we would set up the test. So it tells me right on the face of that meter what my test amps are for a phantom load test on that meter, okay, for full load. Then you see over there to the right of that K sub H. Well, we're talking about kilowatts, kilowatt hours, right, is how we get paid. So that's just showing you for that meter, it's 1.8 kilowatt hours. I get this question asked a lot, K sub H versus K sub T. Well, the K sub T is a testing constant, and these days, almost always, they're the same thing. Now, I've in the past, years and years ago, I've actually seen on the face of the meter a K sub H and a K sub T that were different, okay? So you go by the K sub T to test that meter. In this case, it gives you just a K sub H there. So what that's saying is that back from the old revolution days, when one complete spin and turn of my disc meant that I'd used 1.8 watts. Okay, when I saw 1.8 watts used, and then of course the faster it's spinning, that's watt hours, means I'm using more power faster, right? So the disc would spin faster. Now we use pulses, obviously, but it's still the same thing of 1.8 watts. Now it's per pulse. Okay? Right, kilowatts. So, excuse me. So I got 1.8 kilowatts per pulse. Whenever I get a pulse on there, that's telling me, so you've heard before when you've hooked up and it's beeping really fast on you, that means it's using more power faster. Okay? So then in last over here to the right, it's just showing that it is a Y configuration over on the far right over there. Y. So all of this information is right here on the face of the meter, right? We're back here. Okay. So all of this, that's the same exact meter I got all this off of, okay? Now, when you're going to make your connections in that, I'll talk about this real quick, then I'm going to jump over to CTs since it's on here. This is where we pick up our pulses, okay? You were talking about that 1.8, okay, watts per pulse. Well, when we do a test on this meter, we need somehow to be able to pick up the pulses and measure them, because what we're doing is we're saying, okay, you pulsed and that should have been 1.8 watts. I'll do a measurement and I will say, was it 1.8 watts? And that's the standard customer load test on a meter. So that you would make that test and you would say, okay, I want to see how accurate this is using the CTs that are feeding this and the customer feeding it, but here's how I pick it up. So I just go right on there. This is a magnetic pickup that pops on the front of that communications port to pick it up. If it was coming out of the face somewhere in my pulses, then I use the elastic band and I get the blue snake and move it on there. Okay, but here's how you pick up your pulses right here with that magnetic pickup on the front. All right? So let's talk about CTs for a second. CTs are current transformers, and for us, when we're out there in the field, for all of us, they're step-down transformers, so they're taking a lot of current up at the top of the pole, and they're transforming it down for us to work with at the bottom of the pole. Okay? And on all of these, on the side of them, they'll have a number written on the side of them, which is going to be the ratio for them. In this case, on the side of these, if you look on it, it has 200 written on the side of it. What that's saying is this is a 200 to 5 step-down current transformer. So that means if I run 200 amps through here, on my secondary terminals out here, I'll see 5 amps, and that's the ratio. If I run 200 through here, I'll see 5. If I run 100 through here, I'll see 2.5 across here. So that is the ratio of 200 to 5 or 40 to 1 is the ratio of primary current, which is in here, to the secondary current over here. And that's why when you test these, you have to measure your primary current and your secondary current, and you do a comparison of those and see how close they are with that CT out in service. How close is it to that 205 ratio, which is what it's supposed to be. So can they see the flexes? So in this case, I'm using this to pick up my primary current, and then over here is my secondary current. So I'm doing a comparison of here to here, and I want to see how close is that to 200 to 5. Okay? Now on the nameplate of the transformer, you can see right here, the one that I'm looking at on the screen here, it's a Durham product. The stuff that gets good for us is you go down there to where it says ACC class. So that is the accuracy class of this current transformer, and it says the accuracy class for this one is 0.3 at 0.5. Those numbers are, the accuracy class is 0.3% accurate at 0.5 ohms. The two things that hurt a CT are heat and burden or resistance. We just call it burden when we're talking about CTs, but it's resistance. Excuse me. So if I put more resistance on there, I know my accuracy is going to go bad, and if I get them too hot. So right here it's saying the accuracy class is 0.3% at 0.5 ohms. If I add more resistance to it, that accuracy is going to go down, okay? And then you'll also notice just to the right of that, or actually we'll look just below it real quick. 60 hertz again, because we're ANSI here, US, so we're a 60 hertz system. You see NSV 0.6, okay? That's the nominal system voltage, okay? What that's saying is 0.6 kilovolts comes out to 600 volts. So it's saying that this CT is made to work on a 600 volt circuit, 600 volt system, okay? Now, if you go to the right and just above that, you see RF 3.0. That means the rating factor is 3 on this. The CT manufacturers have come out with this to try and help you. You don't have to stock as many CTs on the shelf as you did before. Because what they're saying is with a rating factor of 3, if this is a 200 to 5 CT, I can use it all the way up to a 600 amp application. So 3 times the rating on it, okay? Now, something to keep in mind, we talked about 20 amps, a class 20 meter. So 20 amps seems like it's a key number, and we're going to talk about our test switches here in a minute that are actually rated 20 amps. So what happens is, if you think about this, if I have remember I said always on my secondary side I'm going to have 5 amps at the most. So on a 200 to 5 CT, the most I should have should be 5 on my secondary side, right? If I get 200 amps in there, I'll have 5. Well, if I start bumping up that rating factor, the CT is made to work at that. I can go to 400 to 5. If I double it, my secondary current doubles as well. So if it's a 200 to 5 CT and I put 400 on it, I've now got 10 amps on the secondary. So think about it. If I go up 3, I'll have 15. That's why your rating factors max out at 4, because 4 times 5 is 20, and my stuff's rated for 20 amps down there, my test switches and stuff. So that's why the rating factor stopped at 4, because if I've got 5 on the secondary and I bump it up 4 times, I'll have 20 that could be possibly coming out that secondary side, okay? And since everything's rated 20 amps, we ceiling at 4 for a rating factor. In this case, it would be 3 times the rating factor, so I could use it up to a 600 amp application. And notice we mentioned before how important temperature is, right? So it's saying at 30 degrees C ambient. So that's all. As long as it stays there or below on the temperature, it's fine. But once again, if you start heating them up, the accuracy starts going in the toilet, okay? And then last but not least, down in that bottom right-hand corner, that BIL, that is a number, that voltage level right there is if you would get enough voltage and it would actually arc across there and damage that transformer, okay? Hopefully you never deal with that. So these are the CTs that we're dealing with right here, okay? So they're the current transformers. What they're doing is they're taking the primary current and they're stepping it down to more acceptable levels down here for my meter, both for safety's sake and the size of all these switches and everything, okay, and easier to measure. So now we have PTs, they're over here, which are potential transformers. They do the same thing with voltage that the CTs did with current, because we want to keep that power at the bottom of the pole, and power is just voltage times current, right? Power is VA. So if I can keep the voltage down and the current down, I have less power at the pole, and it makes it safer for all of us to work, okay? So here you can see on a PT, here's a label on a PT, and the same thing you see down there, accuracy class 0.3 at W. Well, don't ask me why, but the PT folks make you have to look up what a W is and what an X is. They don't actually give you a number. They have a chart that correspond to these letters are numbers. So they're saying the accuracy class for this PT, it's 0.3, okay, at 0.3% accurate at this W, okay. And then, so we have the next slide here, which is, and there are those ratings. So W in this case is 12.5 VA. If I double it up, you'll notice that my accuracy level also halved, right? I went from 0.3 to 0.6. So you can see here, when I went up to 25 VA, when I went up to the X, that it's saying the more power that I put on it, the less accurate it is. So that is my voltage transformer over here, or my potential transformer over here. So you've heard them say called VTs or PTs. So this is bringing my voltage down so that it's at levels that are easier for us to work with, safe for us to work with, and I can have smaller equipment down here at the bottom of the pole. Okay? So let's just talk a little bit about down here at the test switch and what the test switch involved in this. Test switches, I've been to a lot of different utilities, and the color coding and the test switches are always different. I've never seen the same color coding. Sometimes I'll get in there, that's no. Sometimes it'll be close, but they'll at least be off by one, but usually more than that. So the color coding is going to be different at every utility company. And these test switches, absolutely. By the way, none of this is hot. Okay, I should have said that to begin with. Sorry about that. So I've got nothing hot here except for the screen over there. And but nothing, I don't have anything hot here, so it's safe for me not to have my stuff on. All right. So you can see here, these test switches also are different. All right, I got a lot of different test switches, but one thing you'll know, these phenolic barriers they're always going to have between the voltages, between the different phases on the voltages, because they don't want you going phase to phase on any of the voltages. So these phenolics here are always going to be there. Some cases you will have the shunt. The short stroke blade is always the shunt blade. That is the blade that when you open up that shunt blade, you've now shunted the current coming from the CTs, from over here, to the meter. So I have now shunted that current coming to them, so it's safe for me to work. So if I shunt all of 3 phases, then I can go up there and feel a lot safer when I go to pull that meter, right? So here are my shunts. My short stroke blades are the shunt blades, okay? And then the longer blades that have the duckbills in them are the return blades. And they always have that plus-looking connector right there for these duckbills to go in, okay? So the duckbills always go in here. So that, is always your return blade. It's a longer stroked blade. And you've heard me talk about when you make your connections to do a phantom load test in the field with your push connectors here with the hooks. When I go put that easy hook on there, I'm always going at the bottom down here, so I'm always going at the bottom of the return blade. Okay, so my returns are the long stroke blades. My short stroke blades are the shunt blades, always, okay? And then over here, the duckbill, and I don't know if everybody calls them duckbills. Let's see, I heard in Florida, Sneaky Pete's. The only other one I've heard is, if you haven't heard my Mexico story, when I was in Mexico, the first time I was down there, I know a little bit of Spanish, so I thought I'd be slick and learn how to say duckbill in Spanish. The only problem was they didn't call them duckbills down there, but I didn't know that. So every time I would say duckbill, pico de pato, I'd notice them looking at each other kind of weird, and I was like, okay, well, when I finally get them out and they can see them. But then when they got them out and saw them, they all just started laughing and looking at me, and I didn't know what was going on. They call them dead fingers down there, dedos tontos, so they don't call them duckbills. So remember, they don't speak English, so I was literally telling them to take a duck's bill and stick it in the test switch right here. So that was the joke for a while. They teased me about the whole pico de pato. I guess that's how they thought we cooked ducks in Tennessee, but we're going to stick with, we're going to go with duckbill, not dead fingers and not Sneaky Pete's. And the point of this is, this just allows me to go in there and get in series and see the same current that meter is seeing with my test kit. So essentially, I just need an in and out, a flow in here. And that's why there's a layer of insulation right there between the top and bottom, between the black and white here, so I can get an in and out flow. Okay, so it's always in the white and back out the black. In the white, back out the black. So when I put it in here, the flow of the current comes from the meter, from the CTs. It comes into the shunt blades, goes through the meter, and then when it comes back down, it hits the white, goes white to the test kit, back out the black, and then just back to the return. So it's just allowing me to peek in and see the same current that meter is seeing. Okay? So that's how we make our connections here. I would say, please, always make sure you shunt first before you connect your duckbills. Okay? Always shunt first. Removing or taking them in or out, always shunt first with those, okay? Before you put these in here. Okay? And then after you get those out and you close these back in, then go ahead and close those in last, okay? For my voltages, to pick up my secondary voltages here, because I'm counting, excuse me, I'm counting the pulses with that pickup. Remember, we put it on the front. So if I can count my pulses and I can look at my voltage and my current, I can test this meter doing a customer load test, right? So what I need to do is pick up my voltages. So when you connect your voltages, it's alligator clips here, and the order that should always do it is you're removing them. Leave the white on last, leave my neutral last, and when I make my connections, I always connect my neutral first. Okay? And then I would always recommend left to right, right to left. I don't care, but just get an order of doing it one way or the other, and you'll make less mistakes, okay? So I'm always just red, yellow, blue. A, B, and C. So remember, these are going to be different. That you could have on your test switch, it could be, see a lot of these, it could be shunt return, your two CT switches. I could have my return over here next to my shunt blade. So I would have my two oranges here, so that would be one phase. So I'd have phase A for my shunt and return. So my CT connections for just phase A. And then I could maybe have the voltage for phase A. Then I would have a phenolic. But if not, I could have them separated. Just I could have shunt and return, shunt and return, shunt and return, all three of them in a row, and then my three voltages in a row. So you can have a lot of differences. Just remember, those phenolics are going to be between your voltages, okay, on there. And I would make sure you take a look at the switch, and if you haven't seen it before, and figure out the layout on it, okay? Because that's very important to us when we start doing this field testing. All right? Sure.
Tell me about billing multipliers.
A lot of folks I've talked with out there have told me that they write them on the inside of the cans. So on the inside of the can door, you'll have a billing multiplier written. What that is remember, we talked about you are transforming down. We're stepping down all this stuff at the top of the pole. But that's what the customer's actually using. So yeah, we step it all down so that we can use these smaller switches and this stuff, and then we build them. But to build them back, we have to multiply back up, or we transform down. So I'll just give you, for instance, if you have a 600 to 5, right? So if you have a 600 to 5 transformer, then you would take 5 and divide it into 600, right? And let's see, you get 120. So it really is 120 to 1. So if I get ready to do the billing multiplier on there, when I have transformed it down at the bottom of the pole and I took my measurements now, I'm going to have to multiply by 120 times whatever I get to take it back up to what that primary current was up top. So I have to multiply by that. And let's say I've got a 2 to 1 PT involved also. Then I got to multiply by 2. So in that case, if I had a 2 to 1 PT and a 600 to 5 CT up there that I was using, I've got to multiply that by 120 times 2. I've got to multiply by 240, whatever the billing numbers I get, to get back to what the customer is actually using. And that's why billing multipliers are so important. And we have on, when you set up a site with ours, there's a place to put a billing multiplier that you can double check it, because you can think you don't have to have that much of a mistake or leave a number off, and you're multiplying by big numbers. Okay, so a mistake on a billing multiplier usually costs you a lot of money. Okay? Good question, Chris.
You know, why are there so many different wiring colors and test switch colors? What's going on there?
Well, every utility back in the day, at some time, they established what their colors were. But the colors should always follow not only from the handles, but the actual wire colors. So what it is, it allows you as a meter tech, you can track something. You can see what phase by the wire color. I know what color I should have on a phase. So when I start tracking where it's going up to the CTs and coming back from the CTs, I should be able to track these colors. So when I've got this orange coming out here, right? So this is my shunt blade, right? So my orange wire here is leaving out of here. So it's coming from the CTs. It's coming from my CTs here. My black wire here, it's coming to my CT, and it's feeding my CT. And as it comes into the CT, it comes into the meter, then this orange wire that comes it comes back out of the meter here, and this is my return going down here. So you can actually trace your wires. It allows you to trace the wires if it is correct by the wire color. So this is in on my A phase, and this is coming out of my A phase current going back towards the CT again on my return.
Got a 9S meter socket. I've got a whole bunch of potential stabs there right in the middle. Why is there so many potential stabs there?
Well, a typical 9S service, you got to think about all the connectors you've got on that. I've got A, B, C, neutral, and ground. So I've got all these different connections I've got. It's the simplest one because you have all these connections that are made, right? I'm not using a B phase voltage as a reference or doing anything. It's all very straightforward. A, B, C, neutral, and ground. But I have to have plenty of connections. I have to have a lot more connections on a 9S meter than I do on, let's say, like a 3S. So I have to have more stabs to be able to accommodate all that.
Right. So you got A, B, and C, and then you got neutral all the way over there on the right. But what are those three potential stabs in between A, B, C, and the neutral?
KYZ pickup. If you do use a KYZ pickup, I've only used it maybe twice in all this time I've been here. But if you use a KYZ pickup, it's where you've got your switches and relays in there. Use those little tiny little easy hooks to get on there and make your connections. And if it's set up that that's how you're maintaining your pulses is with a KYZ pickup, then that's why you have to have those extra stabs in there. Pickup for the KYZ. Good question, Chris.
So you mentioned that using on the CTs, we can use a flexible current probe on a 600 volt CT.
Sure.
What if that CT is a high voltage or a CT PT combo? How would I test that in the field?
Then you would use one of the horseshoes you see everybody use, which mounts on the end of an extendo stick, and it's high voltage. This is not considered a high voltage probe. That's rated for 230 kV phase to ground or 433 phase to phase kV. So it would be for using in substations for overhead stuff because it mounts on the end of an extendo stick. And it's definitely got a higher rating on it, like I said, using substations or anything like that, get up on that primary. And I didn't mention this earlier, but we always talk about that checking and the billing multipliers and that. When I was talking about the CT and what was written on the side of it, there are times when it might be stenciled on the side of that CT. It says 200 on the side of it, and it's actually a 405 CT. So when I was talking about that earlier, I meant to say that. Sorry about that. And you don't. This is all you do a visual test of what's going on, but you actually have to confirm it because you can't trust your eyes and what's on the side of something. I mean, I've got pictures of them where it's 400 right here on the side of it, and every one of them is an 805 CT. So you can't assume anything. Your eyes help you with what you test out there. It's like we've said before here in the bunker, we're like forensics guys. We're looking for the mistakes, and then once we know there's a mistake, why? What's the cause of the mistake so we can fix it? And you can definitely see mislabeled CTs out there.
What if your utility doesn't have test switches? How can I interface to that meter?
Good question. Let me go over here and grab real quick. Yeah, if you go to utility companies and they do not have the test switch here, you have the option of using different probes to pick up your currents, but you also have, and you've seen it one of our other ones, I don't see it. We have a meter adapter that you can also plug in that will provide you a test switch at the bottom of it. So you can take that meter adapter, pull the meter, put it in the meter adapter, and then when you insert the whole thing in, it's actually got a test switch at the bottom of the adapter. Or if you need to use other probes to pick up your currents, you can do it that way as well. But no, there wouldn't be any difference in the wiring. There wouldn't be any difference in the wiring. As far as your color coding and all that, everything would stay the same. Yeah, but like I said, there's two different ways of accomplishing it if you don't have the test switch. I can use these other smaller probes to pick up my currents, or I can take that adapter, plug it in the adapter, and put the whole thing in here, and it has a test switch at the bottom of it.
Mark also asked if he could walk us through the connections on a 3S and a 4S meter over there on the far right.
Yep.
We could talk about a 3S, obviously.
Yeah. So let's see, how do we want to do this? Is that all? Okay, so you see here on this switch right here, oh, nothing's hot right here. So you can see that that's got to be my voltage. It's a long stroke with no connector to go in it. That's my short stroke. So I've got 2 voltages and 1 current, right? So when you pick the test setup, you're going to pick the one that has 2 voltages and 1 current and 1 PC, 1 primary current, because there's going to be one place that we're going to actually use our flex to be able to CT and probe it, right? So when you're picking out your service types, remember, PC on there is primary current, which typically correlates with where you're going to put your flex probes. So in this case, I would just make my 1 connection right here. I would go my duct bill in right there. I would close this back in right here, and I would have my A and B phases connected here and here for my voltages.
We've seen in the field before that it's pretty rare for us to find a single phase 3-wire using a 3S with a test switch. And so most guys typically use a test switch adapter that John was referring to, or using a clamp-ons to directly connect to the secondary. A lot of times these 3S meters are used for very light commercial load. We see them at ballparks, usually like powering up lights. So it's they probably try to use the cheapest, kind of metering components they can at that site, because it's not a huge amount of revenue. Do you want to briefly talk about the 5S meter socket?
No, not really.
You're going to have to.
Okay. So 5S, when we're talking about deltas on the 5S, what are we always talking about? Typically, A and C phases, right? So we're going to get on A and C phases, and we're going to use B as a reference. So in this case, you'll see here I've got voltage, shunt, return, voltage, shunt, turn, voltage. So
A little unique because typically, when John was showing a 4-wire Y, you have a reference to neutral, and in this case, we're referencing an actual phase, so it's a phase-to-phase voltage. Sorry.
Right, no problem. So over here, I'm on A and C phases, right? Here and here. So I've got, you can see I've got my 2 returns, and I've got my 2 shunt blades right here. So I would be typically for a 5S 3-wire Y delta, right? I would be on my A and C phases right here with my currents. Then I've got my voltages here. And then on a B grounded, you would just ground your B phase. I would ground my B phase, or I may connect my neutral to my B phase to make sure that I get it grounded that way. So here's my A and C phases, right? And then I got here, here, here. So here's A voltage, C voltage. There's my reference. No.
Work on a meter safely without a test switch for shunting. That would be an easy way to do it. But if you didn't have a test switch, you could put a jumper across the CT or the PT at the top, or you could actually just risk it and hoping that the meter contacts make closure. Lisa did mention, when she is correct in the chat, that if you didn't have a meter installed into that socket, and the test switch was not shunted, you could open a CT. That is correct.
Very good.
Yeah. So John, to answer your question, it's a little bit of a challenge because a test switch can ensure your safety 9 times out of 10, but when you do pull that meter, you do run the risk of those contact closures not closing, and it could open a CT. If you, John, what would indication be if a CT is open?
It will start to hum, and it will start humming louder and louder very quickly. So it's similar to, you have to watch it sometimes if we're all connected up and you disconnect, if you've ever heard of someone doing that before, they'll disconnect the cable right there at the test kit. And if they do that, you can also you can open up a CT. So you have to be careful. That it'll climb very quickly and it'll make a really loud noise. Yeah.
We hear a humming noise and
Yes.
we try to put the meter back in quickly or put the CTs back in service.
That's right.
Big Dan also wanted us to review the meter nameplate slide again. Do you mind going over that?
No, meter nameplate right here?
Yes.
Okay. So starting over there up, you're going to have your meter form first. In this case, it's this one right here. So we've got it in a 9S socket right here, 9S service. So we're using it for a 9S there. The class 20 is typically showing you what the amperage is this meter is rated for. And so it also tells you the amperage you're dealing with there at the bottom of the pole when you're working with it. So this is a class 20 for 20 amps. You could say a self-contained meter might be a class 200. And then you could have 200 amps down there at the bottom of the pole you're dealing with. So it just makes you aware of what you're dealing with. The transformer rated meters are all typically going to be a the class 20 for 20 amps. Since you have an exterior step down transformer that's stepping it down for you, then that meter is made to work at 20 amps at a lower amperage. It'll also show you the voltage range that the meter can operate within. So in this one, it's 120 to 277 volt. It'll also tell you if it's a 4-wire Y, 4-wire delta. In this case, it's a 4-wire 60 hertz. In ANSI, that we work with 60. You can go to foreign countries where it's 50 hertz, but in our case, it's 60 hertz here for ANSI in the United States. The TA is what ANSI has deemed to be the full load test amps for this meter. So when you perform that full load power factor light load test, ANSI tells you this is what you should run for the full load. And they're saying here TA or test amps equals 2.5. So it's going to be 2.5 amps for your full load test on this meter, which tells you what your light load is because it's always 1/10 of that. So it would be 0.25 or 1/4 of an amp on the light load for this meter. And then, of course, your power factor test is you run the full load, but you just make your power factor 0.5 really bad. And so with that number there, you can build your phantom load test in your test kit when you see that TA on there, because that tells you where to start, which is your full load. And then K sub H is that's your kilowatt hour constant. We also have what we like to use is K sub T for a testing constant. And all that is saying is, from back in the disk days, it's just saying for this meter, when that disk makes a complete revolution, that's designates it's used 1.8 watts. It spins faster as it's using the power faster, but the constant to use is 1.8. So when you set that up correctly in the test kits, then that'll allow you to get your registration percentages correct. Okay? And then last is just telling you it's a Y service.
Attended my guess the metering error class. You may notice on the nameplate that it says 122.77 volts, and that's a phased and neutral measurement. So if you have a delta service, a 4-wire delta service always has a high leg. So the high leg is typically 208 because it's phase to phase. So phase, 120 volt phase to phase is 208 volts. So if you had a single range meter, if it was just a 120 volt meter and you put this on a 4-wire delta, what would happen to that C element? It would eventually blow. Luckily, most of our solid state meters now are multi-range, where they range anywhere from 69, up to 480 volts, and that can handle any service type you have. But if you have think about older mechanicals or single range solid states, those are a bit more of a challenge if you have these varying potential loads that you may have, which run across on a 4-wire delta. And I'll shut up.
No, it's all good stuff. So I hope you guys got something out of today. We were basically we wanted to go over, if you're just starting out, what are some pointers maybe we could give you, and what's some safe operating procedures on dealing with these meters. and what these different things are on the meter site and up in that meter can. So we also wanted to make sure you understand the next one's coming up, and if you register for all 4, you can get a certificate. We've got vectors coming up. Man, we've got vectors coming up Thursday, next Tuesday, CTs and PTs, and then next Thursday will be justification of site testing. So to get your diploma, you need to register for all 4 of those, and that way you can hang it on the wall there and get the big raise. And we hope that you've gotten something out of today. And please send us in suggestions. We thought that with all the meter schools being closed, that it'd be good for us to do some classes from the meter schools. That's where we came up with this. But we're always looking for suggestions, so please let us know. We take them all very seriously. A lot of the ones we've done over these 9 weeks have been ones you guys have suggested, okay? So we really appreciate that. And I'm not getting any pointers from anybody. Seems like we're okay. So I'm going to close out with a prayer, and then we're going to get out of y'all's hair today. Father, thank you so much for what we're seeing is some relief in our country now. We're starting to see things open back up. There will be a new normal, but we're getting more normal. And Father, we just thank you so much for what you've done to help us get through this, to give us comfort and peace that others just don't know. And Father, that's what I ask right now is we're starting to move forward now, and we're going to get back out there. People are going to be nervous. They're going to wonder how they're supposed to act and what they're supposed to think. But Father, you know you left us the great comfort to be with us. So I just ask that the Holy Spirit would well up in each and every one of us, show us what we should do, what we shouldn't do, and most of all, to be able to reach out and help others. So thank you so much for what your Son did, Jesus Christ, and all these things I say and ask according to the will of the one who paid it all, my brother, Jesus Christ. Amen. Thank y'all, and be careful out there. God bless, and make sure that you're still social distancing and doing all that stuff, because looks like things are starting to open up. So we just really appreciate your support on this, and thank y'all. God bless.